All right. Thanks, Kevin. Well, thanks for the invitation. And like I made it as less provocative as possible by putting the question mark, right? Initial version didn't even have the question mark, so. But anyway, before starting, so I was talking to Philip. Actually, was mentioning it right before my talk. That so in the MT research, there are many universities on the East Coast doing the MT research, let's say, in a large scale. Like Johns Hopkins is one of them, Maryland, and some other places. So, I gotta tell you my qualification as a machine translation researcher first. So I belong to the Korean Institute of Mathematical Sciences, and the Korean Institute is housed in a building called Warren Weaver Hall. And many of you have probably read the Warren Weaver's Memorandum on Translation from 1948. And then, we are housed there. So, it probably makes sense that I do the machine translation research. And then I was like, yeah, that's too weak on evidence. So what would be the next evidence? Turned out that this Warren Weaver Hall is on the street called Mercer. And then Mercer, and I was like, yeah, that's kind of familiar. Where did I hear from? And then that's the Bob Mercer, one of the first papers on the statistical MT from 1991. So I was like, that's the second evidence. But you gotta have, let's say, one more, right? So I was walking around the street and then Warren Weaver Hall, and I was passing by, let's say, one more block away. And there is I found one building, and then that building had a name there of the building. I was like, oh, that sounds really familiar. And then the building's name was Brown Building. And then the first author of that IBM paper was the Peter Brown. So I was like, third evidence. So I gave a Maryland, and then gave a talk, and then at the beginning of the talk, I gave we have the Warren Weaver Hall on the Mercer Street next to the Brown Building. And then Hao Dome told me that if you find the double Della Pietra, I'm going to be super impressed. So I did the Google search. Turned out, nearby in Brooklyn, there's a upscale butcher shop called Della Pietra's. So I think this completes my qualification as a machine translation researcher. So I see that those people who are laughing, who have actually read the machine translation history book, and that's who do not laugh, apparently haven't. All right. So maybe there's something about New York University and machine translation research. So I hope that you're all convinced that, I can do some machine translation. So, machine translation is not a small thing, right? So it's a very big thing, because if you think about translation, you can think about just general translation or the translation for specific domain and so on. And it's been going on since the end of the Second World War, essentially, the research-wise. So there is something like the rule-based machine translation, where I think they are being used in the industry quite well. And then there's a statistical MT, and among them, phrase-based MT seems to be one of the dominant approaches these days. And there's syntax-based MT, and somehow they merge at some point and then split it into hierarchical phrase MT and then syntax-based phrase MT. And then the approach or the paradigm that I'm going to talk about today is the neuro-MT, which is again a part of the statistical MT. But one thing I have to tell you is that this x-axis in this tree, it's not even a tree, but anyway, x-axis is time. And then you might be surprised that I put neuro-MT before the phrase-based or the syntax-based MT. And let me show you why. Interestingly actually, sorry about that. I just made wrong slide. But anyway, statistical machine translation is really simple. It's a very elegant framework for doing machine translation. You want to have a black box machine that's going to read a source sentence in one language, and it's going to generate or spit out a correct translation. And the black box is tuned using existing data. You don't really do much inside. And then, magically with the quite large amount of data, it starts translating. And then it does as well as any of the other approaches that we know of in machine translation. But why did I put neuro-MT before the phrase-based MT? Because the neuro-MT was in fact introduced in 1997 by two research groups simultaneously, and both of them are in Spain on the Mediterranean coast, one from Valencia, and the other from Alicante. So in 1997, Forcada and Neko proposed something called recursive heteroassociative memory that looks exactly like the usual neural machine translation systems we are using. And then I met Forcada, and then I asked him, you found the amazing thing in 1997 before I even started learning how to program. And he said, yeah, we found it. It was really nice, except that, like our computers back then were really not that fast. And we didn't have any GPUs. So I was like, okay, understandable. And then I asked him, there is another paper from another group in Spain in the same year doing the exactly same thing. And then apparently they are all friends. And then they were having a beer at the bar at one point in Spain. I think it was in Valencia. And then they kind of discovered it all together and then wrote the paper separately. But again, Castaño and Casacuberta in 1997 also said that the size of the neural nets required for such applications and consequently the learning time can be prohibitive. So back then in 1997, it was kind of dream of getting this work. But one thing that changes over the last about 20 years is that we now have the computing power and the amount of data to train these kind of models. Because I'm going to talk about the future of machine translation, I'm going to give only a super short 1-minute introduction to NeuroMT today. So NeuroMT is really nothing but one gigantic neural net that consists of the 3 main components. First component is the encoder, and that's a recurrent neural net, or often implemented as a bidirectional recurrent neural net. That's going to read one word at a time, or one symbol at a time, and then update its memory state. And I mean the bidirectional RNN as in you're going to read once in a forward way, and then there's going to be another recurrent neural net that's going to read the sentence in a backward way. And one question here is, okay, how are we going to represent the input, right? Are we going to give a word? Are we going to give a phrase? Are we going to give a characters or anything? But at the end of the day, from the neural net's point of view, it doesn't really matter. So what we do is that we encode the source sentence into a representation that is going to be as neutral as possible. So we usually encode the source sentence as a sequence of words, and each word is a so-called one-hot vector, which is all 0 vector except for one element whose index corresponds to the index of the word in a vocabulary. So it has really no prior information about the word at all. Every single word is equidistant away from every other word. So we have now encoded the source sentence into a sequence of vectors. And the decoder, which is yet another recurrent neural net, is going to look at the source sequence and then start spitting out one word at a time, the translation. Of course, spitting out is not a correct way to describe it. The decoder rather tries to compute the probability of the next target word, given the source sentence, and then all the words before. And then once we have the distribution, what do? We simply select the most likely one, or we sample from it. And then sampling from that distribution is pretty simple. So we have these 2 components, and then in the middle, we have designed something called soft alignment module, or nowadays everyone is calling it attention module. That's probably because it sounds much sexier than the alignment. But this is, again, nothing but a small neural net that's going to look at the source sentence and the target word. But one thing I have to emphasize is that this is just one gigantic connected neural network, or you can call it nonlinear function approximator. And we train this model to maximize the log probability of the correct translation given the source sentence in the parallel corpus we have. And how do we train it? It's the simplest optimization algorithm you can think of, stochastic gradient descent. We make a small step toward the local maximum of this log likelihood for about 2 weeks, and then you get the awesome translation model. So that's like the 1-minute intro to NeuroMT. So people, since 1997, no one has been working on this for about 14 years or 15 years. And then suddenly, somehow in 2013 and 14, different groups in the world started working on this simultaneously without knowing each other working on it. roughly. I think, like Yoshua Benjio knew about, others working on it in Google, just that he never told me so. So we had some asymmetry in the information there. But anyway, we worked on it, and then we just realized that after 15 years, with some advances such as having a soft alignment module, gets us a pretty good results in the translation. So how good is it? So initially, somehow everyone started working with English to French translation. That's probably because we thought it was slightly easier, or at the same time, I was in Montreal, so everyone was able to speak French. So it was pretty easy to go. So in 2014, this is the best performance you could observe in the public domain. And then we started with somewhere, this is the blue score, so higher the better. We started from somewhere here, and then over about a year or half a year, we improved it little by little, and then got to the level of the existing phrase-based MT system. I mean, the best MT system there. And then on English-German, somehow English-German got the most popular after the English-French, because just that the corpus size is slightly smaller, so we can train the model for only a week, and then we get the decent result. We started somewhere around here, around 10 blue score, and then it gradually improved. And then these improvements are not from like only us or only Google, but from the different groups in the world, including Montreal, let's say Google, Stanford, and other places. And then on the WMT15 English-German, we see the similar trend. And then it's getting higher and higher every time. So in other words, and we participated in WMT15 last year on different languages. So we used a single code base, one team of 3 people, 5 language pairs, and none of the members of the team speak neither Czech, German, Finnish, nor English natively. And then somehow we just trained the model using the very same code base, using the different corpora, and then we were able to get somewhere close to the, like very well working system, except for the Finnish to English, where I believe we used the morphese in a wrong way. But we're getting, much better in Finnish to English anyway. So, okay, it's been about 15 minutes I've been talking about. And then after these results, what I can say is that, okay, NeuroMT has rapidly caught up with phrase-based MT, and in many of the languages, we're competing against the phrase-based or the hierarchical phrase-based or the syntax-based MT, neck to neck. Pretty good. And if it was let's say, talk at a conference where the, length is like, I don't know, constrained to 15 minutes or 20 minutes, I could, in effect, finish my talk here and say that yes, let's push further and beat phrase-based MT with the NeuroMT. And then I can say, yeah, thank you. And if you have any questions, please do tell me. Yeah, that would have been fun for me, but not fun for the audience, and especially the audience in Johns Hopkins University, where, like everyone knows MT much more than I do. So, yes, was there a question? No, okay, all right. Yeah, I mean, like no question, yeah, so this is just for fun, all right. And then, like we spent like a year really hard on making the NeuroMT work as well as the phrase-based or the hierarchical phrase-based model. And then at one point, I just realized that this is a nice game to play. So I work on NeuroMT, making NeuroMT as work as well as the phrase-based MT. And then over the next 10 years, I'm going to add something every year that's going to push, I don't know, like 0.5 to 1 blue score up. And then, 10 years, then I'll probably have already gotten my tenure, and then I can continue doing that for like 20 more years until I, like do something else, right? But I just realized that, yeah, this is a nice game, but is this actually the real game that we need to play? So the game that we are playing is on the table, but is it really the game that I want to play for the next 10 years? Maybe we are not playing a real game. Maybe we are looking at a very tiny corner of the whole stadium. Maybe we're not playing a real game, and then we need to look at what the real game is. Maybe this is time we look at the real game. The reason why I started thinking about it is that on some language pairs, NeuroMT is doing slightly better than phrase-based models. Some other language pairs, the other way around. I guess there are a few language pairs that the rule-based MT systems are doing better than both of them. But they are like really similar to each other. Like I see the difference of blue 1, blue 2, and then of course somebody have to ask now, okay, so what does it mean to have one system that is better than the other system by the blue point of 1. I'm not even sure if that actually matters too much. So I decided to look at, okay, how the machine translation systems work in general. So let's look at the example. So this is, I don't know, some comments I took from IMDb. So if I were to translate this whole paragraph into French, then I'm going to take a first sentence, and I'm going to do some kind of word segmentation or tokenization or, you know, like all those normalization. And then I get this sequence of words. And then the sequence of words is fed into the machine translation system, which will spit out the sequence of words in the target language. And then that sequence of words are the normalized words. So I want to do the detokenization, you know, desegmentation, all those denormalization to make it look like the actual sentence. And I put it back there. So I got the first translation of the first sentence of my paragraph. And I'm going to do it for the second one, third one, fourth one, and so on. And I saw like 3 issues there. First is that, okay, it's been done in word level. And because I was born in Korea and raised in Korea, I know that the words are not really that well defined. And also it's done sentence-wise. And also it's just a bilingual translation almost always. And, you know, like, does anyone agree that these 3 are issues? Or is it possible that nobody agrees and that these issues are only to me? Can we do some survey? So raise your hand if you find these 3 things as issues in machine translation. All right, yes, about half to 2/3. Okay, I'm in a good track. And then the nice thing about NeuroMT, or the part that NeuroMT can outshine existing machine translation system, somehow corresponds exactly to these 3 issues I have seen. And then I thought, okay, maybe what we need to do is not to try to play the same game that has been played for the past, let's say, 2 decades. Instead, let's bring the game to the next level, to the actual stadium, where we're going to play a slightly more realistic game. So let's talk about the word level first. So one thing I told you about NeuroMT is that from the neural net's perspective, as long as you encode it as a sequence of vectors, it doesn't really matter whether it's a word, characters, I don't know, some other symbols that you want to use, Unicode, bytes, phrases, they are all same thing. So instead of doing the word level translation, I ask, can we do it character level or the subword level translation? But of course, there are, so before saying that, I gotta tell you, what are the issues that I see with the word level modeling. First, this is a one word in Korean. And that corresponds to Ministry of Trade, Industry, and Energy. And in order to understand this, you have to segment it first, and then understand that, okay, this is industry, trade, energy, and ministry. And then ordering is like completely messed up. You see that, right? Because it's not the trade industry, but industry trade. But when it's translated into English, it's like trade, industry, and energy. The reason is that it just sounds better. So there is some issue with the word level modeling unless you can do the very good segmentation. It's actually unclear. And I'm not even sure if this is supposed to be the gold segmentation. Because some people are going to put these two, let's say, energy and ministry into a single segment. Also, when we look at the word level modeling, what happens is that all these different words, like the run, runner, ran, running, are kind of considered independent from each other. Whereas we know that that is completely not true, right? Run, that's a verb for running. Runner is the person who's running. Ran is, like past tense, and running can be two things, all right? But they are all related to each other in the actual meaning of a meaning. And furthermore, although I don't speak Chinese, in some languages such as Chinese, sometimes there is no blank space at all. So I asked my Chinese-speaking colleague to give me like one sentence. I don't know what it means, but I cannot even tell if this is a one word, few words, or I don't know, like as many as 8 words. You cannot really tell that. And people have to use the Chinese segmentation algorithm to segment it into words and then, do the translation. But then I have to ask, okay, how did you actually build a Chinese segmentation such that it's going to maximize the translation quality? Did anybody actually think about it before they built the segmentation algorithm? Not sure. Furthermore, it's the era of the social media. I use Facebook quite a lot. I believe a lot of people here use either Facebook or Twitter, I don't know. And somebody's probably checking Facebook at the moment on their laptops. And then if you look at those, language there, you see huge number of typos, and you don't really care too much when you write it there, right? And then with the word level modeling, now that brings in a very big problem. So of course you can always do the spell checking and then, correct the typo first and then do the translation. But I think that's kind of weird to do so. Because as a person, even if there are a few typos, I just read it and then, I have no issue with, however, what kind of word that is. But I don't need a separate thing like spell checker or the typo corrector first, and then I read it and then understand it, right? It doesn't look like that's a necessary component there. So then can we use something smaller? Yes, with NeuroMT. So we can train a language model using the word, and then we get some kind of continuous vectors. Use the characters, we get some kind of continuous vectors. We can use the sub-characters, which I'm going to talk about later on. And the thing is that the neural nets don't really care. And then this kind of transition started not by me, but by people at University of Edinburgh a year ago, or half a year ago. Senrich et al. In 2015, around October, wrote a paper called Subword Level Neural Machine Translation. And then what they proposed was that, okay, we're going to do the neural machine translation using the existing code base downloaded from the public. But now, instead of feeding in the corpus as usual, we're going to separate the words into a character n-grams. And then how do we get the character n-grams? We're going to just do the offline pre-processing once, and then get the most frequent character n-grams. And then it's super simple, right? You just read it once, and then they wrote the code in Python, 30 lines, that was it. And that was actually awesome because apparently you can write a 30-line Python code, and then you can get the results that is publishable and awesome. And then really awesome. So I use this almost every day, And then what it turned out that the neural net, in this case, not only does the translation by word, but it actually does some kind of transcription, even though it has never seen that kind of thing before. Because it got the rule not only at the word level, but also at the subword level, or the morpheme level, or however you call it. And it was not even morpheme because they tried with the morph-SL, which didn't really work for them. So they just gathered the character level and character n-grams based on the frequency, and then it just worked out. And at the same time, people from New York University and people from CMU decided that the words are not that great with the neural net. So let's go for character level, at least when we read it. When we generate it, okay, we'll go for word level because everyone thinks that the generating a very long character level sequence that is coherent is difficult. So some people from NYU, for instance, Yoon Kim et al., decided that, in the language model, instead of reading a word as a single entity, we're going to read it as a sequence of characters, which are going to be read by the convolutional neural net and followed by a very deep highway networks. Turned out that this model can work very well on the languages such as Turkish and German, which is quite understandable, according to many of the people who know natural languages. But me, I'm not sure. Well, we'll see. And then similarly, Ling et al. And Ballesteros et al. Tried the same thing with the recurrent neural net instead of the convolutional neural net. And I started to work on character level right around time. And then, 2 weeks later, a group from CMU, led by Chris Dyer, published a paper saying that hey, we can do the character level neural machine translation by simply inverting or making it upside down of this model in the decoder. So you're going to say that, okay, this is the word, but now instead of writing down as word, you're going to use the recurrent neural net to put the one character at a time, and then so on. But of course, this model had a big issue. It still relied on the explicit segmentation in advance. And then the segment, yes, please.
Just for a sake of argument.
Yeah.
So phrase-based systems can include several units as well. Why do you think that makes sense for a system?
Yeah, so that's actually, thanks for the question. So the issue with the count-based models is that you run into the data sparsity issue. And then if you think about the phrase-based systems or the n-gram language models, you never really go over 12 or 13, right? You go for like 7. So phrase-based system, usually 7 words phrase up to. And n-gram language models on English, like 5, 6, sometimes people use like 8. And one of the reasons is that you run into the issue of data sparsity because you don't really get to see the very long phrase ever. Whereas the neural net language model, because we project everything into the continuous space, it can generalize much better to the unseen n-grams. And then if you cut it down into the sub-character level, everything gets much longer, a lot longer. And then the existing count-based models will run into more trouble than the neural net-based model. And I'm pretty sure the character-level phrase-based machine translation is not going to work unless you're going to have your phrase table like 10 or 20 terabytes with the even larger corpus. But I don't think it's going to work well. Philip, care to chip in? Right. Yes. Okay, great. Yes. So 2 people agree, so I guess that kind of gives the idea. But still, the thing is that this one uses the segmentation, explicit segmentation into the words or the, like some kind of units. And then I don't like it because, okay, how do people even make the segmentation algorithm when they are not considering what is going to be used for? So we decided that wait, why do people think that the character level generation is difficult? So that was the end of the last year. And then we started wondering, is it because people just think that's difficult? Or have they tried and it didn't work? And we started to try to figure out why people think like that. And then we couldn't come up with any reason. We couldn't come up with why people think that's difficult. So we decided that, yeah, let's try. Because it doesn't look like there is any reason not to do so. Let's try. So this is some preliminary results. We're trying to, submit a paper to ACL soon. So we decided that source side, we are going to use the subword level by the Rico Sanrich et al. From last year. But the target side, we are going to try both their approach and simple character level sequence. The recurrent neural net in the decoder side is going to spit out 1 character at a time. No changes. Of course, we kind of changed the architecture. We tried something that is more advanced. Turned out that it doesn't really help. Just a very basic thing. English to German, if we do the BPE to BPE, we get 21 blue. BPE to character, 20. English to Finnish, in fact, we get much better. English to Russian, yeah, they're neck to neck. English to Czech, we get somehow much better. This one is still training. It's taking a bit long. So turned out that we can just generate the character level model, and then you can generate it. And then when we visualize what's going on inside, we see the kind of soft boundary between the subword level units, and also the attention mechanism shows that, given a subword, it's going to use the same kind of attention weight for every character in a single unit. I wanted to put some figure, but I had some issue with my IPython notebook yesterday, so I couldn't do it. For instance, a phrase called Spar Garden in English apparently is translated into Kurpark in German. Kurpark? Yeah, Spa Garden. Yeah. That's from the news test, by the way, Dev said. But that's apparently Kurpark, okay, according to the reference translation. And this model actually is Kurpark? I don't know German, by the way. Yeah, I don't know any of the languages that I'm talking about. So it splits the Kurpark automatically, and then Kur part is going to be aligned to the spa, and then Park part is going to be aligned to the garden. And it's all character level, by the way, on the way. So what's happening now here is that we started from the word level, and then we are moving toward the purely character level without any kind of pre-processing. And then what we see is that it's possible. And then when I drew this figure, when I was drawing this figure, one thing that reminded me was what happened to the computer vision or the object recognition community about 2 years ago. People were, using the SIFT descriptor initially, and then put the support vector machine on top of that. Later on, they used the SIFT, and then use the Fisher vectors or the whatever the sparse coding to make it into a gigantic feature vector, and then fed it into the support vector machine. And then they use the, sparse coding or the RBM directly on these pixels, and then fed it into these support vector machines. And eventually what happened is that they just built a one neural net that's going to read the pixel values directly and do the object recognition. And this transition looks super similar to what happened there. So maybe we might get something much better in terms of translation quality if we go all the way to the character, so that the whole system, starting from the source character to the target character, is tuned completely to maximize the translation quality instead of having a separate modules there. But then, I got contacted by Samsung on, trying to do some collaboration, and then Samsung people told me that Professor Joe, we have some issue with the character level processing, because in Korean, we have more characters than the words. And then, wait, is that true? And then I started thinking about it. That is true, because each character or the letter in Korean is a composite of the one consonant, vowel, plus an optional consonant. So in total, there are 40 consonants and vowels. But once you start, combining them together, we get huge amount of characters. And that's why Korean apparently takes the most space in the Unicode, and it doesn't really help. So it essentially increases vocabulary. So we decided, with the master students at the Center for Data Science at NYU, we decided that let's go for the sub-characters then. So we are looking at the Chinese and Korean to decompose a character or the letter into, for instance, in Chinese, radical and the remaining, or few of them, and then consider them as the input. We're still working on it. Hopefully it's going to work out. So this is the character level thing that we need to work on now. So this is a new rule of the game where I'm going to throw you the characters sequence, try to translate it into the character sequence again. So next new rule is the larger context. Oh, yes?
So when you go all the way down from word to character or sub-character, do you imagine having to change the architecture or change the hyperparameters in some way, or are you arguing that same thing?
So for Korean, I think it's going to work as it is. For Chinese, there's some issue because the sub-characters are also characters. So maybe it's better to give some kind of, let's say, boundary for the, beginning of one character, end of one character. But otherwise, I think it's going to work as it is, but up to the level that we are achieving with the just usual character or the word level. But in order to go further, maybe we need something more. That's how I think. Yes?
What about the pixel level?
Yeah, exactly. So when was it? So I gave a talk at the group meeting for the first time when I moved to NYU, at the beginning of last semester. And then I gave a talk, and then Jan LeCun was like, yeah, Joe, I think you should use the pixel level and then ConvNet first, and then do the translation. I don't think that's the best way to go, efficiency-wise, yes. Yeah.
Well, if efficiency weren't an issue, but it'd be the best way to go.
Sorry?
Let's suppose efficiency weren't an issue.
So
is there a reason based on statistics on generalization to think that you should actually memorize chunks like a particular character,
right,
or for that matter, a particular morpheme word or phrase?
Right. So if we don't care about efficiency, in fact, the best thing I think we can do is to go for the pixel level, for the, let's say, input. For the output is to go for the stroke, or the, how we actually write it down directly. Yeah.
It's not obvious that you don't also want parameters associated with higher level chunks.
Well, the recurrent neural net parameters. So recurrent neural net should take care of that higher level thing, right?
Only sort of.
Yeah.
There's kind of a type token distinction.
Right, we can talk about it later, yes. So any questions? I'm moving on to the next one. Oh, yeah.
Character models eat up a longer amount of information to decode compared to a word-based model. Is computationally more?
Yeah, that's super good point. So it's computationally slightly more expensive, The reason is that in the word level or the subword level modeling, the most of the computation is in computing the so-called softmax output at each time step, computing the probability over every single token or word in the vocabulary every time. Whereas in this case, the length gets much larger, but at each time step, the softmax computation is much smaller. It's actually tiny compared to the existing ones. So okay, I'll move on to yeah, for the computational reason, in fact.
So this maybe crystallizes the downside of working character by character. So there's work, as you know, but not everybody in the audience maybe knows, on reducing the expense of computing the partition function of the vocabulary by using hierarchical softmax. In other words, you predict the next word one hit at a time. And usually for that to work well, you have to do some kind of clustering. So that when you predict that the first step you go left or right, that's going to be a division between like nouns and verbs, and then it's between animate and inanimate, or something that makes sense like that, so that based on the context, you could actually make a reasonable prediction. The prediction that you're making, on the contrary, is this a word that starts with the letter B or the letter C? And those aren't natural categories. And so I wonder if you have any insight into how it is that the machine translation system is able to work as well as an ordinary language model that knows that the word banana and the word cherry have similar embeddings, even though one starts with B and one starts with C. Whereas other words that start with C would start with other words that class with C. It just seems very hard to predict the next character because it's approximating a like sum x over the whole subset of the vocabulary that starts with that letter.
Right. So if it was the Markov model, where it's going to be conditioned on the very short history, and then looking at only B, and then trying to predict A, because it's going to be banana, it's going to be very difficult, because, how are you going to not go for a bar or a pub, not pub is wrong, but anyway, or Baltimore, it's difficult. But now, what's important here is that this process of, where did the decoder go? Oops, sorry. So the process of decoding in the recurrent neural net is not not step by step, if you think about it, because of the continuous memory vector that is carried over. So it has a continuous state that is carried over. So let's say it wants to say something related to fruits, then the continuous vector is going to say that it's about fruit, but for the first word, it starts with banana this time. And then given that I'm talking about something fruit, and with the B as B already decoded, it's going to be A. And then based on that, because it's fruit, it's not going to go for L and say Baltimore, it's going to go for N. So the hidden state of the recurrent neural net is where all the magic lives, essentially.
That's certainly true. I guess my question is whether it's still a little bit surprising that it works, because the embedding for the letter B doesn't mean a lot by itself in the same way as word level embeddings would. And so it's a little surprising that this doesn't work without several characters to look ahead. You can imagine doing it character by character, but doing look ahead before you do normalization. It's also, the other reason that it's surprising is as I understand it, in hierarchical softmax, the structure of the tree actually does matter. Whereas here, the structure of the tree is given to you by this fairly arbitrary letter-based trie. And so you didn't get to pick it in a way that would give you reasonable stepwise representation.
Yeah. So being surprised, I totally agree. That's why everyone, I think, thought that the character level decoding is not going to work without, let's say, explicit segmentation. In the case of this model, they actually do the explicit segmentation, and then there is a vector that actually defines the word first. And then given that, it tries to generate the character sequence corresponding that. Yes, right. So that's why I think everyone, based on your kind of reasoning, I think everyone thought that, it's going to be difficult. But what I see is that this recurrent neural net is surprisingly more powerful than we often imagine. And then the hidden state can actually encode the structures that we believe are necessary for generating out the character sequence. So yes, surprising. Yes, agrees. Yeah. All right, so let's go to the larger context. So, let's talk about Q&A for a second. So question and answering. Almost every single question and answer that you're going to see is very difficult to answer if you don't have the context. Where did James go after he went to the grocery store? Answer candidate, his desk, I think that was his desk, but his freezer, a fast food restaurant, his room. Nobody can answer this. It's just impossible to answer. But as soon as I throw you a context in which the question was answered, it becomes super straightforward. He went to a fast food restaurant because you read this whole context paragraph. And it's not only for the Q&A, but for anything that you can think of, context always matters. Think about the question answering as a language model. We can turn this question into James went to blank after he went to the grocery store. And then filling in that blank is essentially a language model. And in order to do what it means is that in order to do the language model well, you want to have context. And context helps. So, for instance, what it tells, okay, this is a very bad example because I couldn't fill it up myself. But anyway, the context essentially tells us what the theme or the topic of the document is. And in practice, this corresponds to what are the words that are more likely to appear in this document. So we tried it out on a language model, very simple recurrent neural net language model, where we try to predict the next word, given the whole history. And when we do so, we gave to the recurrent neural net a previous, some n sentences. We varied from, let's say, 1 to 8. And then we tried like the really simple naive approach. But of course, the naive approach didn't work out well, so we had to change the LSTM slightly a bit so that we separate out the current sentence, let's say I called it like intra-sentence dependencies by the memory cell of the LSTM, while the intra-sentence dependency is going to be only integrated at the output of the long short-term memory units. So we call it late fusion. And turned out that, it's quite obvious that it's going to work. At least it's not going to hurt. Because the worst case, the model can learn to put the zero weight to all the previous context. But thankfully, that didn't help. We tried it on 3 small corpora. And because of use of the small corpora, this paper was rejected. But we see that every time we increase the context number of the context sentences, we get a decrease in the perplexity, meaning a better predictability of the next word by the language model. But, my student brought me these figures, and I was like, so what does that mean? So can you explain me why it helps? And he was like, I don't know, it's a neural net, it just works. I trained it for some time on the cluster, and I was like, all right, but that's not enough, So let's do the simplest analysis we can ever do. So we looked at how the perplexity changes with respect to the number of context sentences, and then we did it per part of speech tag. So I do not believe in part of speech myself, the existence of it, but I just had to do it because that was the simplest thing I can find. And what we see is that the so-called open class words become much more predictable. Whereas the closed class word or the functional words, you don't see much difference, or sometimes it gets slightly worse, or sometimes it gets slightly better. Which kind of agrees well with my conjecture that this is the theme or the topic that matters a lot. Like much of the functional words don't really contribute to the theme or the topic of the document, whereas those open class words are the ones that are decided well by the theme, right? So, any question at this point? I think, Jason, you have something or no? Okay.
Yeah, what do you mean you don't believe in first?
Yes, so, okay. So, a lot of the terminologies or the concepts from the synthetic theory of language, I don't know, sometimes I get just confused too much. Yeah, so that's what I meant. I get confused. That is possible. That is one possibility, but I'm not ruling out that they are not the thing as well. Yes. So it's going to be either they are not a thing or I don't understand it. And, I don't know. I give it like 50-50 out for now. Yes. But any other things, yes. Yeah, so do I believe in words? Not really as well, as I said earlier, yes. I actually believe in phrases more than words. Okay. So, okay, you're saying something? Yeah.
Well, I'm debating debating whether to say this, but there's some history in topic-based language modeling that has some of the same insights. So Sanjay, I think, is not here right now, but 10, 15 years ago, he was getting good results with larger context language modeling that made use of the content words in longer context to
right.
sharpen the posterior over the topic.
Right. Yeah. I think we cited that paper and a few others from the old, let's say, literature. Not only on the language model as in artificial language modeling, but there is some work from the education side where people are saying that having a context, helps on these things or something like that. So we just cited. I didn't read it carefully. But anyway, so larger context machine translation now. It becomes super simple if you think about it. We're going to just condition on the source side context and then target side previous translations. Of course, it turned out that it's much more complicated because now we have two different types of context. Context that we have generated, the model has generated itself, and the context that is given by the source. And we have the both past context in the source side and the future context. How are we going to make a model to use all of them as well as possible? Turned out it's not that trivial. And then we are working on it, but hopefully it's going to work out pretty well. And then eventually, what I think is really important is doing the dialogue level machine translation. Because in the dialogue, it's super straightforward that, knowing what is being talked about in this conversation is going to help us really narrow down what is the correct, let's say, choice of the words in current sentence. And people have been working on this kind of hierarchical recurrent neural net model for dialogue modeling. And then all I need to do will be to put another things here and here and here and here in another language. We'll see. But still, dialogue level machine translation is still limited because you know about the context of the conversation, but you don't know about the word itself. So the ultimate thing that we want to do, I believe, in machine translation or natural language processing or Q&A is to in fact do the translation based on the word knowledge as well. So if I know about the general topic of the translation, then it's going to be easier. If you talk to professional translators, they actually do some background survey before they do the actual translation. When they do the simultaneous interpretation, they actually study about the topic in advance, and that helps. And you can think of this kind of word knowledge as the kind of background knowledge or the background study that people do. And this goes directly to the Q&A as well. So I'm going to now move on to the issue of the bilingual translation. Is there any question before that? Or the comments? I'm open to comments always. Yeah, Kevin.
So now you're moving to characters and you're also moving to full documents, and so you might see long sequences.
Yeah.
How is it else do you remember when you remember everything?
That's why I mentioned about the hierarchical recurrent neural net. So what we want, I think, eventually is that we have a recurrent neural net for the chapters. Let's think about a book, chapters, recurrent neural net for the sections, subsections, paragraphs, and then so on. Of course, how are we going to train it? That's actually a big issue that I'm running into these days. So I'm talking to NVIDIA people to speed it up first, or memory-wise. And at the same time, there has to be a way to train this model much more efficiently than just relying on the backpropagation through time with the SGD. I don't think that's the answer there at the document level. Okay. So, this is actually my favorite part here. So multilingual translation. So some people believe that there is something called positive language transfer. I found the 2 books talking about the positive language transfer. I found 2 books talking about the negative language transfer. So it was on, whether to teach your kids to be bilingual or not. And then some say, yes, you should. Some say no. So it's an unsolved question for humans, and for machines, it's not solved as well. And then the issue is that the existing table-based method, it's difficult to make it multilingual unless you do certain kind of, let's say, you build a table here, you build a table here, trying to map it each other and do a lot of heuristics. But nice thing about this neural net model is that you just plug them in. You're going to plug the N encoders corresponding to N source languages. You're going to plug in M target decoders for the M target languages. And eventually you get a single model for the n by m language pairs. And of course, the first issue you run into is that there is no like usual, let's say, multi-way parallel corpus. So we don't want that. We don't want to be constrained by that. And then, like if we just do it naively, we get the quadratic explosion of the number of parameters because just there are quadratic number of the pairs. And of course, there is a question of whether this is going to work at all. That's the biggest question. And if you think about the naive way of doing the neural machine translation, just put the whole sentence into a vector and then translate it from it. It's pretty straightforward. In fact, the Luong et al. Did exactly this and then showed that this helps, but doesn't really help in their paper. And then the issue is that we want to use the attention mechanism because that is the one that made whole neural machine translation work. But the thing is that is the alignment specific to language pair or not? And everyone I was talking to before this January was telling me that of course it's language pair specific. So you have to have the separate alignment for every language pair you run into. And I was like, but that's not that great. And like if you look at the humans, that must not be true because there are some person who knows like 10 languages, apparently here, right? Who knows 10 languages, and then their, let's say, brain size is not like 10 by 10. So, okay, 100 times larger than us, and it still works. So there has to be a way to make it work for the multiple language pairs by sharing the still same model. But everyone was telling me that, that's not true. And then Dong et al. From Baidu thought that, like if it's not specific, then we're going to just use a simpler model. If you make it 1 to n, it's simple. You're going to just have the n attention mechanisms there. And then, but like me and my collaborators, we were kind of stubborn, and then we thought, I think it's going to work. Why not? So we decided that, okay, let's do it. So we put the shared attention, so one attention mechanism or the alignment mechanism, and then we put English encoder, English decoder, French decoder, German decoder, Finnish decoder, French encoder, German encoder, and Finnish encoder. So we just plug everything in and then train the model using every single parallel corpus available from the WMT15. Of course, it took a lot of time. We had to use multiple GPUs and so on. So it took us like 10 months, not to train single model, but to, to get every experiments out. And then turned out that it works. Okay, so for different language pairs, there are some ups and downs. But in general, it was doing as well as let's say, in this case, 10 single pair models. Of course, for some it was doing better, for some it was doing worse, and so on. But in general, we saw that in fact, without the quadratic explosion of the parameters, we can train a model that's going to work on the multiple languages simultaneously. And we're like, okay, but this is great, but they are just doing okay. What is the place that we'll be able to see the positive language transfer? And turned out that in the case of low resource language pairs, when we have the low resource pairs, it helps to have the high resource pairs together when train the model. And we tried with the English to Finnish, German to, this is English, German, no, Finnish to English, German to English, English to German, with different settings, and turned out that doing the multilingual thing is always beneficial. And this one is not from us, so I'll just skip. I'm running out of time, I guess. So eventually, what do we want to do in this term of multilingual thing? In fact, the multilingual is just the first step into the multimodality and multitask learning. And then we have been using this neural machine translation model, not only for the translation, but for image caption generation, video description generation, speech recognition, all the same code, the same model. And then eventually, now that we have seen that the multilingual translation works, what we want to do is that we want to build one model that's going to be able to take us into German, just a natural image, English, or speech, and then to translate into English, Finnish, speech, or image, or so on. And people have been working on each of the modalities separately, and it's about time to plug all those in and then see how well it works. So I think, like this is kind of like the new territory that we want to move on to in terms of machine translation. We want to do character level translation with a much larger context than a single sentence, with the multiple languages in consideration simultaneously. And I think that's going to be our new game. And I think it's a very exciting and fun place to play around with. So, wait, are there many grad students, like the junior grad students here? Just one question. Only one? Why, you guys should encourage the junior PhD students to come here. Come to talk. But okay.
You just exposed something we didn't know.
But anyway, yeah, so, well, that's it. And then, thank you. And if you have questions or the comments, especially comments, I'm always open to listen to comments and then integrate it into my model to make it better. So, yes, please go ahead. All right, thank you. Yeah. Mm-hmm. This one? Oops, sorry. Okay. Yeah, I don't remember actually putting animation here, but somehow.
Are you saying that the language agnostic sentence space is a side effect of the model?
Yeah, it is a side.
That is not something you're modeling?
No, we are not explicitly modeling this. Yes, Jason.
Well, so I have a follow-up on that. It seems like what you would really want to get something like this is something maybe the attention model had. So you would like, when you're reading English, to be able to identify parts of, to be able to basically label parts of the English sentence with semantic roles in a way that the attention model can pick up on them. And maybe the state of the LSTM or the RNet is actually encoding something like the roles that particular words are playing. You could do it with some other kind of latent structure, which is maybe more explicit tree.
Right.
Maybe that's why it works. Is that a reasonable intuition?
Yeah, so what I think is that so it's doing translation reasonably. Okay, it's not doing amazing translation. I think amazing translation is like about 50 years away. Amazing as in, translate my paper and then I can submit it and get it accepted. But what I see is that, okay, if this one is doing a reasonable translation, and then if we believe that there are certain latent structures that are necessary for doing the reasonable structure, then this model has somehow captured that. And I think the question actually that slightly different, but the next step question is, what are those things that this model has captured? I think it's time to actually, torture this model and then figure out what has been captured. And then for that, I need your help. Collaboration always welcome, because as I said, I don't even believe in the existence of part of speech tag, and I don't even know what to look for, but I think there is something that we definitely want to try to look at. Yes. Yeah.
So just to be clear, your shared attention is over the concatenated variables over all the encoders, right?
No. One at a time. So our source sentence is going to be one of these, let's say 5, I'm missing Russian here, 5 languages. And then, so if it was English encoder is going to read it. And then let's say I want to translate it into German, then I'm going to use the shared attention between English encoder and German decoder.
It's kind of confusing because of I assume that the decoders were producing the different, or we already changed everything on the language, so.
Yeah. Yeah, I know.
Like to some extent, the shared attention may interfere with that because the English decoder may produce a certain word which may appear in this position for French, that the parameters for the shared attention may point to the same.
So, okay, let me point out the one potential extreme case that's going to make it like super clear is that let's say the models have learned to use, let's say, 4 bits or the 2 bits in the hidden state to indicate which source language it is or which encoder it is. And then that bit is going to be used by the attention mechanism. And then decoder is going to do the same thing. And the attention mechanism looks at the decoder's hidden state and encoder's hidden state. So in the worst case, it can have some kind of explicit memory that indicates which source language it is, which target language that is, and attention mechanism is going to look at okay, source language this, target language that. I'm going to use this part of the function to compute the alignment. So that is a possibility.
And it's the same simplistic alignment model that the version of it.
Yeah. Yeah, I'm using the same code ever since, except that, I rewrote once, but it's the same model. Yes. Okay.
If there's any value in any kind of linguistic analysis and data that would help things?
There is. So I believe there are two different ways. First one is the one that I was talking about when I was answering the JSONs. So one thing that we need to do is to actually analyze the model itself using the linguistic knowledge we have, and then trying to see what are the things that were necessary here. So this is a black box, right? And then somehow it's doing something reasonable. And then if we believe that, there are certain things that are required to do so, this is doing something. So then what is it that it's doing? Okay, that's one thing. And then second way is to, that's not my favorite way, by the way, is to actually use those linguistic structures that we have extracted, separately as the target, as one of the tasks in the multitask setting in this model. Let's say, you have the gold standard of parse tree for every single sentence in your parallel corpus, for instance. Then what you can do is that instead of trying to use that as an input, because sometimes you don't have those parse trees, sometimes your parser is really bad, so that it's going to hurt only, you can try to have the, let's say, parse decoder here. And then let's say you train the model, and what it happens is that you're essentially forcing the hidden states or the latent structures of the model to be predictive of the parse structure that we believe is important. Then once that is encoded here, then the other decoders will be able to use this. So I think that's one possible way we can go, and I think that's going to be useful for the very low resource language pairs. Yes?
You put it this a little bit in the beginning, but I don't think you
Okay.
So you were saying that like changes in blue score, it's difficult to say what they mean, and I thought because you're going 50 years ahead, do you think we should, what is our objective? Is log y given x really the best thing? And so we're using this sort of as a surrogate because we want to actually get 2 points.
Right.
But even though there are problems with 2,
Yeah, I mean, so.
Machinery, if we're kind of marching towards this,
Right.
that we don't quite believe in.
So, okay, my innermost myself actually says that there is probably no correct evaluation metric for translation. Even the human evaluators, I don't think they are going to be perfect because, let's say, without any context, evaluating the translation can only be very mechanical, right? Literal translation is the only thing that's going to make much sense. What I think should all this, any kind of natural language processing algorithms or the tasks should be evaluated on is based on the downstream actual application. Let's say, I'm going to drop myself with my translator. Let's say I'm going to use the English to Finnish, actually, I lived in Finland, so that doesn't make, okay, Russian translator. I'm going to bring that. I'm going to throw myself into one village in Siberia. And, can I actually survive there without knowing a single word in Russian, but using this translation system? If I can, I think the translation system is the good one. So so one of the things that, parse tree or the power of speech I was talking about, so, okay, I don't really believe that they don't exist. Otherwise it doesn't make sense to have all those, let's say, actual work that has been done so far. But what I think is that, okay, let's say I do the parsing, then I think the actual evaluation, eventual evaluation should be, okay, so I did the parsing, I got the parse tree, I'm using it for the translation, and then what was the translation accuracy? So those things, I think those are the evaluation, and in that regard, blue, log likelihood, whatever is probably a very rough surrogate we have. Yeah, probably so. But the thing is that we're really low in that metric, so it's really bad. But if we go, I don't know, 70, then we probably don't see anything between 70, 60. Yeah, that's what yes.
This is a slightly technical question. So across, I assume because the shared attention has the same parameters across all you shuffle sentences across different language pairs? Because it feels like if you do a lot of English first, and then French, and then German, and then Finnish, you might lose.
Yeah, we shuffled. we shuffled. Like we went for the round robin style. Like for this update, we're going to use English to French, and then French to English. So what we did was to actually split the different language pairs onto different GPUs, so that each GPU is at each time each GPU is going to use one language pair. So we can split it into, let's say, 3-4 GPUs, and then they run it simultaneously. So yeah, one at a time doesn't really work. Yes.
Since different languages have different similarities, do you think it's helpful if we do a clustering of the languages into a hierarchical tiers?
Right. So if we can actually measure the similarities between different languages, yes, I think so. But what I think is that eventually, if we tease out this trained model, and then we'll be able to tell which ones are actually similar to each other. So perhaps the other way around, maybe. All right. Thank you.